Okay, this hour we will talk about how to find the optimized value of linear equation parameters. Okay, since we have these two formula, the first one is that we have a linear model, which is y hat equals to theta 0 plus theta 1 times xi. Okay, that is very simple. That is exactly the same as y equals ax plus b. Okay, we just use another notation, theta 0 and theta 1. Okay, and the other one is that we would like to calculate the MS value, which is the square area value of the arrows, the average square area value, okay, of the arrows. Okay. So we simply just put this y hat value in the MSE, right? So the result is that right here we put the y hat value, which is the model output, which is the y hat right here. And we simply just expand it to this form, okay? And as we can see that since we have 20 points, okay, in this example we have 20 points, so n equals 20, and we have 20 x1 value and y value, right? So in this formula, n is known value, right? xi is known value, xi, and yi is known value. So basically, okay, MSE, it has two parameters, only theta 0 and theta 1. And as we can see that there's a square value right here, right? Square value. So we'd like to analyze the MS value, okay? So we first take a look at a simplified example. For example, if this one is x, and that is f of x equals y, and if x, okay, is something like polynomial, okay, it has square, right? And we know the shape of this line, if this y line, may looks like this, right? So it may look like this. Okay, so think about this new MSE function. Okay, we draw it in another way. Okay, MSE is a function of theta 0 and theta 1. Okay, and it has several different factors, but it is 0, 1 square plus something, okay, 0, theta 0 square plus something, okay, theta 1, theta 0 plus something, okay, theta 1 plus something, theta 0 plus something. Basically, you can view MSE as some kind of theta 1 and theta 0's function. And it has square right here, right? Square right here. So we can imagine that, okay? If that is theta 0, this x-axis is theta 1, and that is MSE function of theta 0 and theta 1. Because it has square right here, right? So it should looks like a basin. Sorry. It's a 3D basin. Okay, okay. There should be some smallest point right here, and that is a basin. Okay. I'm not sure if you can, or it like a ball. Okay, because MSE is a function of theta 0 and theta 1, and the form of the theta 0 and theta 1, they have a square right here, so it should look like a basin. It's very similar to what I draw. Okay, if you have a x and fx, and it is some kind of it should look like a curve, right? But we extend it into a two variable theta 1 and theta 2. It should look like a basin. Okay, and after that we can if we use all the value in that data table, we have 20 data points, right? And we have 20x1 and 20y. We just put all the value in this formula. The result should be like this, and this formula is a basin, is a ball. Okay, and it should looks like this one. Okay, it should look like this one. But so that exit is MSE. Okay, it is a function of a and b. Okay, because y equals ax plus b, right? And this exit is b, or we say it should be or theta 0. It depends on what kind of it depends. It's really depends on how the what kind of notation you use. Okay, and that is a or theta 1. Okay, so it should looks like this, and because we know it is the term is convex function, and because it is a convex function, so it should have a minimum value of MSE. Because it's a minima, so we use MSE star. Okay, but we don't know, currently we don't know which A star and B star would have the smallest MSE. Okay, we don't know that. So the problem is, how do we find such kind of A star and B star to find the smallest MSE star? There are several different ways to do such kind of things. Okay, for example, again, okay, we use a simplified example. If there is an x and there's a fx, and it should look like this, right? There's always the smallest minimum x value right here, right? You say there is always a value, okay, which is smallest f, right? But there should be a x star, and the value of f x star is the smallest f, or we say it is y. Okay, smallest y star, right? But how do we find such kind of things? In high school, okay, usually we do differentiation, right? So that should be 2ax plus b, and we make it to be 0 so that we can find, so we can find x equals to minus b, right? So that is the smallest value, because the reason we do differentiation is because the tangent line right here equals 0. It has no slope, right? That's what we do in high school. Okay, but right here again, okay, again, If you want to calculate the smallest value of MSE, there's at this data point, okay, at this data point, the smallest data point, okay, right here. The tangent line at B exit should be 0. Maybe this place, this line. The exit, the tangent line at A exit should be 0, something like that. Because this MSE value would be the slowest, the smallest value, okay, in this basin, in this ball, right? Smallest value. So its tangent line, no matter it's at B direction or A direction, it should be both 0. So basically, we should do partial differentiation for A and for B direction. And both their value should be 0. In this case, we can figure out where is A and B. It's very similar to what we have done in high school. We use differentiation to find the lowest point of a curve. But we have multi-dimension right here, so we have the A direction and B direction, so we need to do partial differentiation for A and for B, and so on and so forth. Because then you take a look at this. We want to find the relationship between X and Y, right? X and Y, and in this case we have only one x1, right? And for such kind of linear relationship, okay, to describe the relationship between a feature and a target, we need 2 parameters, right? And in these 2 parameters, in the space of MSE, we can plot them, this value in a 3-dimension way space. Okay, so if we have m dimension, there should be m plus 1 parameters, and then we can plot their MSE value in m plus 2 space, right? Think about it, okay? If we have only 1 dimension, we have 2 parameters, A and B, and we can plot it in a 3-dimensional space, including A and B and its corresponding MSE. So if we have m dimension, we have m plus 1 parameters, and we can plot this MSE function in m plus 2 space. And in this such kind of m plus 2 space, you can find the smallest MSE value, and so on and so forth, so on and so forth. Okay, so basically you can in a m plus 2 space, you can perform m plus 1 partial differentiation. So you can use this m plus 1 equation to figure out what is the exact value of A and B and C, or theta 0, theta 1, theta 2, theta m. Okay, but as we mentioned before, that is the correct way, the most precise way to figure out what is the A star, B star, or we say theta 0 star, theta 1 star, theta 2 star to theta m star, to find the smallest MSE star. But as we mentioned before, in our class, the number of dimensions we used should be few hundred, or maybe 90 or 30, 20, few hundred. You have to think about one thing. It is very difficult to do few hundred partial differentiation, and then use this value equals 0, right, to figure out what is m0, theta 0, theta 1, theta 2, theta 3 to theta m. It is very difficult to do so. So most of the time, we don't use partial differentiation to solve A, to figure out what is the exact value of A and B, and what is the minimum value of MSE. It is doable, but we don't do so because it is too complex. The computation will be quite large to do such kind of things. So in most of the machine learning and data mining algorithm, we use another approach called gradient descent to figure out what is the value of MSE star and A star, B star. Okay? So again, let's take a look at this figure. Okay? So again, okay. So in order not to do this one, okay, we move it to here. In order not to do partial differentiation, okay, we take several few steps. Okay, the first one is the first one is you simply just random. Okay, this one should be here. We simply just randomly select a pair of A T0, B T0. Random is like one data point. Okay, it calls theta t equals 0, right? Simply select this one, and then we use this A value and B value and put it into the MSE. We can get the MSE value right here, but it apparently not the smallest MSE value, right? So we simply just do, again, we do tangent line at the B direction and A direction. For B direction, it should be right here. For the A direction, it should be right here. Again, in the previous example, again, if you want to find this smallest X star, so it has smallest Y star, okay? First, you can randomly select one point on the X axis, and of course you can see that this value is not the smallest. It's not the smallest MSE value, but you can do tangent line right here, and the next step you'd like to take is to go to the opposite direction of the tangent line, which is the left. So next time you select a smaller X, and because you know you go to the opposite direction of the tangent line, so it guarantees its corresponding Y, which is the MS, which is the Y value, will be smaller. And again, here's the tangent line, right? So go to the opposite direction, which is the left hand side, and here you can obtain a new X, and again the tangent line, and you go to the left. So basically for convex curve, okay, the process should be like this: left hand side, left hand side, left hand side. Okay, the wrong direction, right? Because the tangent line now becomes here, and you should go back again, go back, and you simply just jump between the curve, and you gradually close to the x star. So that is the way we find the x star value. You don't have to do partial differentiation, okay, because we have too many dimensions need to do. So in this case, in two-dimension case, okay, again, we will go to next point, right? That is theta t, and right here, okay, we know for b direction we need to go to the negative side, and for the a direction to the negative side. So again, so we gradually goes to the a star and b star. So that would be a star and b star, which is a theta star. That is called gradient descent. By using the tangent line, we can know which direction we should go to in the next step, and so on, so on, so on, so forth. So we gradually close to the optimized value of a and b. So with the optimized a and b, there will be an optimized line, which is right here, right? Because we have an optimized a and b, so we have optimized value model, which has an optimized MSE value, smallest MSE value. That is how we use gradient descent to find the optimized parameters in our model. We don't do partial differentiation because it needs too many computations. Because if we have m features and we have to do m+1 partial differentiations and try to figure out those values of all the parameters, that is crazy. Okay, so we use gradient descent to solve such kind of finding optimized parameter problems. Okay, so I'd like to show you how do we interpret these things. Okay, that is the MSE function, right? So basically we have n, we have all the we already have all the n value and x value in our training data. So that is so MSE is a function of theta 1 and theta 2. Okay, so that's it. For theta 0, for example, t equals 0. Okay, in order to find the next theta 0, t equals 1, then we have to do we do partial differentiation for 0. Okay, that means find tangent line. Okay, so that is the direction of the tangent line. Okay, so the minus right here, that is the opposite direction, so that is the tangent line. So the minus means the opposite direction. Okay, so the gamma right here, the gamma is sometimes we call learning rate. Okay, that gamma value specify if you take a look at the red tangent line. Okay, that is the red tangent line. So the minus means the dot, the red dot. Okay, and the gamma right here is how long, what is the step span you would like to take to jump from T0 to T1. So that is the span of your step. Okay, that is gamma. If gamma is larger, then you okay, so let's take a look at this one. If your gamma is larger, that means every time you take the next step, the span will be larger, okay? But if your gamma is smaller, that means every time you jump, okay, you take only a small steps. It's really depend on your decision. If you choose a large gamma, and it will be much quicker to find the small area, the small value of this curve. Right? Because you can jump far, right? But if you choose a small gamma, that means you need to take a few steps, several few more steps to find the smallest value. But you can jump in a fine-grained way, right? So you have a more chance to find the smallest value rather than use a bigger gamma. And we will talk about how to choose this gamma, and there are several different policies to fine-tune this gamma in the later class. Okay, but currently we simply just know, okay, it jumps to next next value with this gamma. Okay, so that is the actual value of this our example. Okay, so basically the lowest MAC value is right here. Okay, so basically if you randomly choose some AT0 BT0 right here, and it will gradually goes to this point, lowest point, to find A star and B star. Okay, so that is gradient descent. And I would like to show you an interesting view pictures right here. Okay, this picture has been selected to the most interesting scientific figure, okay, many years ago. So it demonstrates how complex the MSE function is. So basically, it is not a. It depends on how many features you have and how many data points you have. So the shape of the MSE is a little bit different. It can be very complex, like this one. So if you randomly select a parameter AT0 BT0 right here, and you for every step you can gradually follow the tangent, the opposite direction of the tangent line, and goes to the lowest value of this MSE curve. Okay, so that is very interesting things. And as we can see that if you choose a bigger gamma, and then every time you jump a little bit far away, but there if you choose a smaller one, okay, then you simply just jump in a more fine-grained way. Okay, but sometimes the convest function, okay, this MSE function looks a little bit weird. So sometimes it has several different we say basin, and that is the local minima. That is the global minima. So if you choose a larger gamma, it may help you to jump out from a local minima basin. But larger gamma may not help you to find the lowest MSE value, because it jumps between here, not here. Okay, so we will teach you. We will tell you how to how to do different policy, different strategy of fine tuning gamma later. Okay. Okay, so that I think that is how do we use gradient descent. Okay, it's right here. How do we use gradient descent to find the optimized value? Oh, we stop right here.